Okay, let's dive right into this explainer and completely demystify the invisible force that literally powers our entire modern world: electricity. Whether you're cramming for an exam or just kind of curious about how your everyday household gadgets actually work, we're going to break down the physics behind the plug today. Now, I know that for a lot of us, the second we see physics formulas or math, our brains just want to shut down. But seriously, don't be intimidated. We've got our friendly robotic guide here to walk you through everything step by step. We're going to make this super logical, very visual, and honestly, completely accessible. So here's a quick look at our agenda. We'll cover the basics of current and voltage, dive into Ohm's law, compare series and parallel circuits, explain the heating effect, and wrap up with calculating power. All right, kicking things off with Section 1, the absolute basics of current and voltage. First up is electric current. Think of it simply as a stream of electrons flowing through a wire over a specific amount of time. It's strictly defined as the rate of flow of charge through a conductor's cross-sectional area. We measure this flow in amperes, or just amps for short. And the formula? Beautifully simple. I equals Q over T. That just means the current is the total charge divided by the time it takes to flow past a certain point. But if current is the flow, what's actually getting it moving in the first place? Well, that's our next concept: potential difference, which you probably know as voltage. Think of voltage as the push. It's the actual, literal work required to move a unit charge from one point to another, like from a battery's higher potential terminal over to its lower one. It's measured in volts, and you calculate it as work done divided by the charge. And the sheer scale we are dealing with here is absolutely mind-blowing. We just mentioned charge, which is measured in coulombs. To put this into perspective, just one single coulomb of charge contains approximately 6 quintillion electrons. Yeah, that's a 6 followed by 18 zeros. So when you hear about just 1 ampere of current, you are talking about 1 coulomb, 6 quintillion electrons, zipping past a single point every single second. Okay, moving right along to Section 2, the golden rule, Ohm's law. So, Ohm's law states that the potential difference across an ideal conductor is proportional to the current flowing through it at a given temperature. Basically, the crucial takeaway here is that if you increase the voltage, that push we just talked about, the current flow increases right along with it, as long as the temperature stays constant. And that gives us the incredibly famous equation V equals I times R, where R stands for resistance. Let's visualize how this plays out. Imagine you're sliding the controls in a circuit simulation. If you've got a 4.5-volt battery pushing against a resistor set to 500 ohms of resistance, you get a tiny current of 9.0 milliamps. If you bump up that voltage slider, the current goes up too. But if you increase the resistance, making it physically harder for those electrons to squeeze through, the current naturally drops. They are completely, perfectly interlinked. And this table brilliantly illustrates our main cast of characters all in one spot. You've got voltage in volts, current in amperes, resistance in ohms, and resistivity in ohm meters. Honestly, you might want to take a quick mental picture or a screenshot of this for your exam prep. It's basically a perfect cheat sheet for the symbols and units you're going to see in pretty much every circuit problem. All right, Section 3. Let's look at how we actually wire things up: series versus parallel circuits. So, there are 2 main ways to wire a circuit. In a series circuit, you have a single continuous path. The electricity literally has to go through every single component in order. But here's the massive catch. If one appliance fails, the entire circuit breaks. Imagine if one light bulb burned out in your kitchen and your whole house went dark. No way, right? That is exactly why household wiring uses parallel circuits. Parallel circuits give you multiple independent paths. If one bulb goes out, the rest stay on perfectly fine because the current just takes alternate routes. And because they're built differently, the math changes too. When you're calculating total or equivalent resistance, series circuits just add up directly: R1 plus R2 plus R3, and so on. The resistance just keeps stacking. But parallel circuits, they use reciprocals. 1 over the total resistance equals the sum of 1 over the individual resistances. In plain English, adding more paths in parallel actually decreases the total resistance, giving the electricity an overall easier path to flow. Now for Section 4, explaining the heating effect. Okay, consider this everyday mystery. You plug in a little space heater. The cord carrying the electricity from the wall to the heater stays completely cool to the touch. But inside, the heating element is glowing red hot. If the exact same electric current is flowing through the whole appliance, Why does only the coil turn red hot while the cord stays totally cool?
Well, it all comes down to the materials. The cord is a fantastic conductor with very low resistance, usually made of copper. But that heating element, it's purposefully made of an alloy like nichrome, which has super high resistance. And the reason that high resistance causes heat is because as the electrons push through that nichrome wire, they're constantly colliding with atoms. These collisions act exactly like friction, rapidly converting electrical energy into thermal energy, and that is the heat you feel.
This whole principle was formalized by the English physicist James Prescott Joule back in the 1840s. Joule's law of heating gives us the formula H equals I squared times R times T. He proved that the heat produced is directly proportional to the square of the current, the resistance, and the time the current flows. That's exactly why a high-resistance alloy, left on for a while, pumps out so much targeted heat.
And finally, Section 5, calculating electric power.
Electric power is just the rate at which electrical energy is consumed or converted, and we measure it in watts. You've definitely seen wattages printed on light bulbs or appliances, right? It tells us exactly how fast that energy is being used. And you can calculate it using any of these three handy equations, depending on what you already know. The foundational one is P equals V times I. Power is voltage times current. But if you mix Ohm's law in there, you can also use P equals I squared times R or P equals V squared divided by R. Let's test this out with a classic trick question. Which has greater resistance, a 100-watt bulb or a 60-watt bulb, assuming they're both plugged into the exact same 220-volt socket? Your instinct might scream the 100-watt bulb. But if we use that formula we just saw, P equals V squared over R, we see that resistance and power are actually inversely proportional when the voltage is constant. Meaning, the lower power bulb, the 60-watt one, actually has the greater resistance. It resists the flow more, lets less current through, and so it uses less power. Finally, ever look at your family's electricity bill? It's not billed in simple watts or joules. It's measured in kilowatt hours. Why? Well, because a joule is a remarkably tiny amount of energy for an entire house. Just one single kilowatt hour is equal to a staggering 3.6 million joules of energy. So if you run a 1,000-watt heater for just 1 hour, you've used 3.6 million joules, and that shows up as just one single commercial unit on your bill. So take a look around your room right now. Which everyday appliances are silently relying on Joule's law of heating to function? Is it your toaster, your hairdryer, maybe the safety fuse in your breaker box? Once you really grasp the building blocks of electricity, voltage, current, resistance, and power, the invisible physics shaping your entire modern life suddenly becomes completely visible. It's not magic. It's just electrons doing exactly what these formulas say they'll do.